Welcome, educators. Thank you for joining me in this session titled Practical Tips in Helping Students with Geometry. My student did well in algebra, so why is he having so much trouble in geometry? Postulates, theorems, constructions, and proofs, oh my! Geometry will help your students to learn to do things decently and in order. May this session be a blessing to you. I think algebra and geometry are some of the most important courses that our high school students will take. They explain and demonstrate reasoning skills. Everything they do in life demands knowing how to get from one place in life to the next. The skills learned in geometry, such as proofs and constructions, train their brains to do just that. So why is it that some students do well in algebra but have such a hard time in geometry, and vice versa? Perhaps it can be explained by using a jigsaw puzzle as an example. Most of us will look at the corner pieces and then all of the edge pieces to make up the outside frame. People who tend to like algebra more will look at the shape of an individual puzzle piece to see if it fits into the next spot. They can do this puzzle just as easily upside down or even backwards because the overall picture doesn't matter until they finish. These are sequential or linear learners. Students who are visual or spatial learners will pick up a piece from the pile and try to figure out exactly where it goes based upon the color or shading of the puzzle piece. They see the whole picture in their heads. Then they break it down enough to find the right pieces. Spatial learners tend to do better in geometry. Algebra is mostly about arithmetic considered abstractly. For example, what happens when we square the sum of two numbers? If you add 2 plus 3 and then square the result, you get 25. But a general way of saying the same thing is that when you square the sum of two numbers, you get the square of the first number plus 2 times the product of the two numbers plus the square of the second number. That sounds complicated, so math people find it more efficient to use variables, symbols to take the place of words, like the first number or the second number. They would say it like this instead: x plus y, in parentheses squared, equals x squared plus 2 times x times y plus y squared. Geometry is more about properties of shapes. Simple examples of properties of shapes are length, area, volume, angles, straight or curved lines, parallel, perpendicular, and intersecting lines. Each area of math develops a lot of jargon and special written symbols, and sometimes students find this confusing. In algebra, variables are commonly single lowercase letters, like A has a value, B has a value, and AB represents the product of A and B. In geometry, a single capital letter is often used for a point in a figure. Capital A has no numerical or quantitative value, and neither does capital B. But AB is used as a sort of variable, not the product of A and B, but the distance from A to B. Algebra people like the end result, whatever it is. They find a bunch of ingredients in the pantry and the refrigerator, they throw them all together and see what happens. Geometry people see a picture of a lasagna and say, I wonder what it would take to make that. Sequential or linear learners make great accountants. Visual or spatial learners make great architects. However, it's important to develop skills in linear learning as well as spatial learning. That is why we require both algebra and geometry for our students. Being well-rounded in both linear and spatial learning will help them to develop skills to be well-rounded in whatever career path they choose. In John chapter 2, Jesus and his mother Mary and his disciples were at a wedding. There were 6 water pots of stone there, and Jesus told the servants to fill them with water. That's sequential. Then he told them to draw it out and bear it unto the governor. The water had turned into wine. Well, in John chapter 4, Jesus tells the woman at the well that whosoever drinketh of the water that I shall give him shall never thirst. The woman then left and went her way into the city and said to the men, Come see a man which told me all things that ever I did. Is not this the Christ? That's spatial. They came to him, and he stayed with them for 2 days, and many believed because of his own word. Let's understand the basics of geometry. The first pace, 1109, sets the tone for the whole course. It is, in my opinion, the most important geometry pace. Fill in the personal geometry handbook and keep it handy throughout the course. Understand some undefined terms. For example, a point is the basic building block of all geometric figures. It has no size or shape. It is labeled with a capital letter in geometry. A line consists of continuous points, but lacks width or height. It is straight and unlimited. It is designated with a lowercase letter. A plane is a flat surface. It is composed of points extending continuously in all directions in 2 dimensions, length and width. It is also designated with a lowercase letter. A solid is a 3-dimensional form consisting of length, width, and height. It has thickness. Let's understand some important defined terms. A line segment is part of a line consisting of 2 endpoints and all points in between those 2 endpoints. It has length, which is measurable. A ray consists of 1 endpoint and all the points along the extension in the direction the ray is drawn. It has unlimited length. Congruent means having the same length or measure. Midpoint. It's a point on a line segment that divides that line segment into 2 congruent parts. Parallel lines. These are lines on a plane that do not intersect. An angle is a figure formed by 2 rays having the same end point. An acute angle is an angle with a measure of less than 90 degrees. I like to think of it as being cute because it's nice and small. Obtuse. An obtuse angle is an angle with a measure greater than 90 degrees. I like to think of the word obese, obtuse. An obtuse angle is an angle with a measure greater than 90 degrees. A right angle is an angle with a measure of exactly 90 degrees. A straight angle. A straight angle is an angle with a measure of exactly 180 degrees. It's like a straight line. A bisector of an angle is a ray with a common endpoint with an angle that divides that angle into 2 congruent angles. Perpendicular lines are lines that intersect at right angles. Adjacent angles are 2 angles that have both a vertex and a side in common, but do not have any interior points in common. They are adjacent, which means right next to each other. Complementary angles are two angles whose measures have a sum of 90 degrees. They are easily recognizable when adjacent. So if you have two angles that are adjacent and you put the two angles right next to each other, they add up to 90 degrees and form a right angle. Supplementary angles are two angles whose measures have a sum of 180 degrees. They are easily recognizable when adjacent. So if you have a straight line and you have an angle that goes along that, the sum of those two measures will form a straight line, 180 degrees. A circle, all the points in a plane that are equidistant from a fixed point called its center. What is the radius? A radius is a line segment from the center of a circle to any point on the circle. Diameter. The diameter is a line segment that passes through the center of a circle with endpoints that lie on the circle. Circumference. The circumference of a circle is the distance around that circle. What are some properties of equality? Well, first of all, there's the addition property. If you have equal quantities that are added to equal quantities, the sums are equal. For instance, if I have A and it's the same size as B, and I add 2 to A and I add 2 to B, then they are still equal. If I have a line segment, if AB is equal to CD, then if I add BC to both of those, then AB plus BC is equal to CD plus BC. If the measure of angle A is equal to the measure of angle B, then the measure of angle A plus the measure of angle C is equal to the measure of angle B plus the measure of angle C. What about the subtraction property? If equal quantities are subtracted from equal quantities, the differences are still equal. If I still have those two objects in my hand and I was to subtract the same amount from both of those objects, they'll still be equal. If A is equal to B, then A minus 6 equals B minus 6. Then there's the multiplication property. If equal quantities are multiplied by equal quantities, the products are equal. If I take those two objects and multiply them by the same amount, they're still equal. If A is equal to B, then A times 4 is equal to B times 4. And the same is true for the division property. If equal quantities are divided by equal quantities, the quotients are equal. If A is equal to B, then A divided by 3 is equal to B divided by 3. Next, we'll learn about postulates. Postulates are statements that are self-evident or seem to be true, but cannot be proven. The postulates in this case should be memorized. A theorem. A theorem is a statement that has been proven to be true in geometry. Let me bring you in a little closer to show you how we do some constructions. And we will start with how to construct a congruent line segment, and then I'll show you how to bisect that line segment. We are now going to learn how to construct a line segment congruent to another line segment. So let's call this line segment AB, and let's construct line segment CD the same size or congruent to AB. So what I need to do is draw a line that's longer than the given line segment. Post a point anywhere on that line that you would like to, and we will label that point C. So now with my compass, I will need to measure the distance from A to B with my compass. And so I'm going to use this, put a little arc right there so I can see exactly how far it is from A to B with my compass. I put that same point on C and draw that arc on this new line that we made, and we will label that point, point D. So now line segment AB is congruent to line segment CD. They are exactly the same size. Next, we can learn how to bisect that line segment. So let's take line segment CD here, and let's see how we would bisect it. To bisect it means to divide it into two equal parts. And so what we would do here is I'm going to take my point here and put it on C and draw an arc. Let's draw an arc right there, and without moving the compass, I'm going to put the point on D and make an arc down here. And then let's do the same thing up above. Without moving the arc, we can place a little arc there. And I can do the same thing on this side, put the point on D, make a little mark there. And then through those two X's, I will draw a line. And that line will bisect CD. If I call this point F, F is the midpoint of line segment CD. On this construction, we are going to make a copy of this angle, and after I make a copy of the angle, we'll bisect the angle. So first of all, with this angle, I'm going to just simply draw another line, and this will be the vertex of my angle, which corresponds to C. Let's call it C prime. And so now I have to figure out, where do I draw this line? I'm not sure, so I'll use my compass to figure out where exactly I'm going to draw that line. So the way I'm going to do that is I'm going to put my point here at C and draw an arc that makes sure I go across both of the sides of that triangle. And so I'm going to come over here now and make an arc that's the same size or larger than that arc that I just drew. So I'll construct that right there. Now what I have to do is I have to measure the size of this angle, the size of this arc. So I did measure, then I'm going to do arc. And let me move that in a little closer. So I've got an arc there. And so I'm going to come over here, and at the same size, I'm going to put that point over here where I cross the line and make an arc. And that gives me a little X there. And so now I know exactly where to draw that line through that X at my point C prime. And now I have an angle that is the same measure as that angle up above, because these arcs are the same size. And so that makes that easy. So now how do you construct the bisector of that angle? We'll call this point A prime here. We'll call this B prime. And so now to construct a bisector of that angle, I'm going to put my point right here where that X was and draw a little arc up there, and then come down and put the point at B prime and draw a little mark there so that it forms an X. Now from my vertex to that X, we will draw a line, and that will be the bisector of this angle. And now, if we call this E, angle A.C.E. is congruent to angle B.C.E. For this construction, we will draw a line that is perpendicular to line CD through point A. So the way I'm going to do this is I'm going to use my compass, and I'm going to come from point A and make two little marks on line CD, one there and one at the other end. And now I'm going to pick up my compass and start at the places where I just drew those X's, and let's draw two arcs down below, one at this side and one from the point over here, and form an X. Now I will draw a line from point A through that X, and it will give me a line that is perpendicular to CD. So now AE is perpendicular to CD, all forming right angles. This time we are going to make a line that is parallel to the given line. So the way we're going to do this is we're going to draw a line through here, and let's make the line parallel to this line to go through this point right here. We can call that point A if we'd like. And so we're going to draw a line that's parallel to this line through point A. So how do we do that? Well, we make a copy of this angle. So let's do that. So I'm going to come over here and put my point at the X, And I'm going to draw an arc. And then I'm going to come and put my point at point A, because that's where we want to draw the parallel line through, and make an arc. Now I'm going to measure that arc. I want to put my point here at the top because that's where my X is. So I'm going to put my point here and measure this arc. So I'll measure the size of this arc to right there and draw a little arc. And then I'm going to come over here and draw that same size arc to form an X. And now, through that X, I'm going to draw a line that will be parallel to the given line through the X. And so I have two lines here now that are parallel. Geometry is perhaps the most important course you will take in school. It trains you how to plan ahead by looking how you got from one place to the next. Everything you do in life is based upon how you got from point A to point B and how you are going to get to point C. That is what the proofs in geometry train you to do well. In the first two geometry paces, we learned some postulates, properties, and definitions. Be sure to keep these up to date in your personal geometry handbooks that are inserted in the middle of each geometry pace. Those postulates, properties, and definitions are used as the reasons why we know the statements are true in each proof. The question we need to ask concerning each statement in the proofs is, how do we know? The first statement is always given in the question, and the last statement is what they are asking us to prove. Each step in between is the process of proving that last statement based on the postulates, properties, and definitions that we have already learned. Let's take a look at this proof from page 1110 on page 18. We have line segment AB is congruent to line segment CD. The first reason is always given because it is given in the question. The second statement says AB is equal to CD. The question we need to ask is, how do we know that if line segment AB is congruent to line segment CD, then AB is equal to CD? Well, a line segment is simply a portion of a line designated by its endpoints. Without the line segment symbol, it is the distance from endpoint to endpoint. Segments are congruent. Distances are equal. So if two segments are congruent, then their distances are equal. That is the definition of congruent line segments. The reason this step is necessary is because we cannot add segments because they don't have a numerical value. We can only add their distances. You will see this step on many of the proofs going forward. BC is equal to BC. How do we know that BC is equal to BC? Well, one of the properties we learned in page 1109 was that if something is equal to itself, it's like seeing a reflection of itself. It is because of the reflexive property. Well, AB plus BC is equal to AB plus BC. How do we know that this is true from the previous statements? Well, since we saw that BC is equal to BC, well, they added AB to both sides of the equation. This is the addition property. It looks also like it could be reflexive property, but we cannot use the reflexive property for links that are added together. So now we see AB plus BC is equal to CD plus BC. What is the difference between this statement and the previous statement? Well, instead of AB, they put CD. How do we know this is true? because a previous statement, number 2, told us that they were equal. So they substituted the CD in place of the AB since they are equal. This is called substitution property. Next, we see that AB plus BC is equal to BC plus CD. What is the difference between this statement and the previous statement? They just switched the order of the two distances after the equal sign. When we switch the order of the addends, it doesn't change its value. For instance, 3 plus 5 equals 8. If I change the order of the addends, I still get the same sum. 5 plus 3 equals 8. This is called the commutative property. AB plus BC equals AC. BC plus CD equals BD. How do we know this is true? In PACE 1109, we learned that if point B is between A and C, and A, B, and C are collinear, see the pencil illustration at the top? Then AB plus BC equals AC. This is called the definition of betweenness of points. Next, AC equals BD. Look at the previous two statements and see if you can see how they came to the conclusion that AC equals BD. Statement number 6 tells us that the two sums are equal to each other. Statement number 7 tells us what those sums are equal to. Now on statement 8, we see that their sums are equal to each other. They simply substituted. AC was substituted for AB plus BC, and BD was substituted for BC plus CD. This is the substitution property. Finally, our last statement says line segment AC is congruent to line segment BD. This is similar to line number 2 above. We proved that the distances were equal, so now we must show that the segments are congruent. Again, this is called the definition of congruent segments. I hope this helps you to get through the rest of your proofs. Asking yourself these important questions, studying the illustrations, and learning your postulates, properties, and definitions will help you. Here's the questions to ask. How do we know this statement is true? What is the difference between this statement and the previous statements? Look at your illustration to help you visualize each statement. Let's learn about the measurements of angles that intersect a circle. Allow me to explain how to find the measure of an angle where each included ray of that angle intersects with a circle. There are 4 main types. The first type has the vertex of the angle right in the center of the circle. It is called a central angle. For a central angle, the measure of the intercepted arc is equal to the measure of the central angle. So if we know that the measure of arc AC is 100 degrees, then the measure of angle ABC is also 100 degrees. Don't you wish they were all this easy? The second type has the vertex of the angle right on the circle itself. It is called an inscribed angle. For an inscribed angle, the measure of the angle is half the measure of the intercepted arc. So if we know that the measure of arc AC is 100 degrees, then the measure of angle B is equal to 1/2 of 100, which is 50 degrees. This illustration is also an inscribed angle because the vertex is on the circle itself. Angle BDK is equal to 1/2 the measure of arc BD. The third type has the vertex of the angle on the outside of the circle. It is called an exterior angle. The measure of an exterior angle is equal to 1/2 the measure of the difference of the measures of the two intercepted arcs. It might look like any of these. On this illustration, if the measure of arc AB is 120 degrees and the measure of arc DC is 10 degrees, then the measure of angle DPC is equal to 1/2 of 120 minus 10, which is equal to 55 degrees. The last type has the vertex of the angle on the inside of the circle. It is called an interior angle. On this one, the sides of the angle must be extended so that they intersect the circle at 4 separate points. The measure of an interior angle is equal to 1/2 the measure of the sum of the measures of the two intercepted arcs. If the measure of arc AE is 100 degrees and the measure of arc BD is 40 degrees, then the measure of angle A.C.E. is equal to 1/2 of 100 plus 40, which is equal to 70 degrees. I hope these points and these tips were helpful to you. I wish I could teach a whole geometry course in less than an hour, but I can't. But I hope that these will give you some ideas and some tips that will help you as you work through the geometry paces. God bless you.